Alright, another draft physics video presentation. Yes, won't be produced. Sadly. Chalk, I do have it. Alright, so I am ready. Mostly. Yeah. How can you be ready? I mean, the whole thing is just so stupid to even have to, have to argue and argue and argue when it really should be obvious to any fair-minded, decently intelligent person. It's just a fact that their answers were silly. They've always been messy and sloppy, and it was just too much of a monoculture, that just forced everybody to just believe, 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 and there just wasn't enough. Let's try to find a better answer. There wasn't any of that, actually. There just wasn't any of it, because the options are so available. They're just sitting there right in front of them in terms of analysis, and you're saying, well, why didn't they just think about that? Because it's right there in front of us. you know. But anyway, so I'll use this video as an excuse to talk about gravity. I wanted to do everything in one video, but just to point out that, I mean, just this simple find a better answer approach finds better answers for everything. I mean, they've gotten everything wrong, not just a few things wrong. It's like everything is wrong. So, I mean, it is startlingly bad physics. So anyway, this is a child, teen, college student, grad student expert. I haven't watched it. Watched a little bit of the child stuff and just said, oh, this is too pathetic. So they're not explaining anything. She's not explaining gravity. Are you really explaining anything? No. It's not an explanation of why there's gravity. It's an explanation of what gravity does, and it's not even an accurate explanation of what gravity does. But frankly, the explanation should be have a great deal of similarity, and I bet her explanations aren't going to have any similarity in terms of even a child can understand these simple concepts. They really can. And the argument is, and the force is so simple that it's almost like you're forced to explain it simply because it's so simple in its function. But let's play along.
Hi, I'm Jan 11. I'm an astrophysicist, and I've been asked to...
So she's one of these frauds, okay, who got her fame by being connected to the LIGO thing. She was their public relations liar, for lying for LIGO. To give us, again, this fake story of what was going on. She never talked about, oh, yeah, the tunnels are 2 miles long, but, we bounced the light back and forth 1,600 times, so, the tunnels were too small. The whole thing was theoretically impossible with just 2 miles worth of tunnel. So, yeah, I mean, we had to, change it entirely. Like we had to 800 times, longer light path. We use mirrors and just bounce the light back and forth, and we somehow know how to make mirrors that are perfect, and they reflect the light from exactly the same location in space every time. Yeah, we have that special. Well, we really don't, but we just pretend we do.
explain gravity in 5 levels of increasing complexity. Gravity seems so familiar and so everyday, and yet it's
so simple. You could just say it's just so simple in what it does. It's just simple equation, simple. It's as simple as a light bulb in reverse. That's how simple it is. You can just think of a light bulb sort of in reverse. If a light bulb was shooting little pushing rays at you, you just think of it exactly the opposite and just think, okay, well, what if they were pulling rays? That's simple in its function.
It's incredibly esoteric, abstract subject.
Yes, no, it's none of that stuff. It's, it really is just as simple as the light bulb. Every piece of matter is doing the exact opposite. Instead of creating more energy like a light bulb, it somehow takes a piece of space and makes that space less energy. Less energy comes out of that piece of space. So every piece of matter is less bright than the background. That's all you have to think of. It just happens to be. The lights are on in the universe and they're off a little bit where the matter is. There. Bingo. Done.
That has shaped the way we view the universe on the largest scale.
Yes, whatever. Now, it really hasn't, but it helped you to say, well, if we're going to make up this stupid axiom, this fundamental premise that's ludicrous, space is bent and warpy and such, then you can make up anything. And that's what you did. You made up everything you could possibly make up. Little black holes that magically found orbits, which they can't do. You know, unless they were born next to each other, they really can't do any of this stuff. They really can't. You can't hit a black hole into something that's going to change its velocity enough to give it an orbit. So it can never be in an orbit.
Has given us the strangest phenomenon in the universe.
Yeah, see, the trick with these light bulbs thing is it's from any distance. The light bulb means that either you crash into the light bulb, the opposite light bulb, the gravity light bulb. You either crash into it because it sucks you in from a distance, or if you miss, you leave again. But you just can't get in an orbit unless you hit something on your way. You have to crash into something, take off a little bit of speed so you don't escape again. So unless you crash into something, you're leaving or you're dying. Those are the only two choices. See, that's one of the facts about gravity. Maybe you wouldn't throw that at a 10-year-old, but you would maybe do it with an 11-year-old.
Like black holes, that has changed the way we look at the entirety of physics.
So again, more blah 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 blah. What does this have to do with gravity? Oh, absolutely nothing, really. The existence of black holes has nothing to do with gravity.
It's really been a
it has to do with stacking matter on top of itself. It has to do with some silly notion that the matter in the universe can be put into one tiny little location. Blah 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 blah. When there's absolutely no evidence you can do that.
Evolution because of gravity.
So, we do have evidence that you can take matter and you can make it pretty dense. That is, you can take matter and turn it into neutrons, and then take those neutrons and stack them next to each other and create pretty dense matter. But black hole? No.
Are you interested in science?
Yes.
Yes?
So this child appears to be quite intelligent for her age.
You are?
Yes.
Do you know what gravity is?
It's something that, so right now, we would be floating if there was no gravity, but since there is gravity, we're sitting right down on these chairs.
Right. So, if she had been, she's watched some science documentaries, no doubt. Articulate answer. But the trick is, right, that gravity's really, the first thing you should say about it is that it exists, okay, out there. All right, and the real thing about the floating part just means, well, if I'm in the same amount of light, if there's the same amount of light hitting me from one side, it's hitting me from the other side, if we use the light analogy, and we think of light as a pushing force, then I don't go anywhere. I'm in equilibrium. Nothing's compelling me to move. And that's gravity. That's all gravity is. More light, less light.
That's pretty good. So gravity wants to attract us to the Earth.
And so again, we're using this silly word, actually. I mean, it's a push. Push is the only rational thing to think exists, okay? Push is so simple and so obvious. Two things in nothing hit each other and they push on each other. They don't do anything else. There's no other function except pushing. And all you can do is take away some of the pushers, right? So if I got 10 pushers on this side and only 2 on this side, you can understand, it's going to move. Push, 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 push. It's so obvious. And again, none of these physicists ever realized, well, push is such a simple concept and pull is so, how the hell do I make a pull? I mean, I have to give this thing arms or something. How do I make this thing, this elemental thing, right? There's not some other elements. There's not little tiny chalk in between the pieces here, right? We don't have little tiny pieces of chalk that I can throw at each other and make something happen. So all I have is this elementally. How the hell do I make a pull? But push, just too obvious. Nobody in physics could do that? Nobody? Ooh.
and the Earth to us. But the Earth is so much bigger that even though we're...
You're right, it has so many more atoms. So that's another thing that you would put on the list of the first things to understand about gravity. Okay, first thing to understand, it's like light bulbs. Okay, just a kind of radiation. You're just saying it's the opposite of radiation. It's unradiation that causes you to move. The absence of. The absence. And, what was I going to just say about that one? All right, so what did she just say? Oh, damn it.
Even though we're actually pulling the Earth a little bit to us, you don't notice it so much.
Okay, so the Earth is attractive. What the hell did I want to say? Oh, it's about the mass, right? So all you can say is it's not the Earth is bigger. The Earth has a whole bunch of little electrons and protons. So gravity's a nuclear force. It moves the nuclear bits, and it moves them more efficiently than any force we know of. So all the, like magnetism, maybe, those kind of things, it moves stuff in such a way as that it'll never feel it, because every part of the thing will be moved. It won't be uneven at all in how it moves you. So you can't be observant to it, because it's not going to move part of you more than it moves some other part of you.
The moon pulls on the Earth a little bit.
Just like...
So again, pull. How does it pull? So they're not explaining anything here. They're just observing and then using kind of juvenile, infantile, silly words, okay, to describe what they see. And they're just silly.
With the ocean tides.
Exactly. Well, the moon is...
So, kid's smart, right? Got the tide part, so that's good. 8 years old, that's pretty good.
Such a big body compared to anything else very nearby that it has the larger effect pulling the water.
So, again, it's this larger effect thing. The sun is gigantic, but not very dense. The gravity, outside the sun's corona even, you just start going a little bit away from the sun, and the gravity starts diminishing rather radically, even though the sun's preposterously far away also. 8 minutes it takes light to get to the stupid thing. We're showing the moon here, but you get it. It's tiny amount of gravity, actually. Very small.
Of the Earth, but
I mean, the moon is having much more of an effect on us in terms of gravitational, okay, in terms of being in a shadow of, than the sun.
More than the moon, think about the sun pulling on the Earth. We orbit the whole sun just the way the Earth pulls on the moon and causes the moon to orbit us. All of those things are acting on you and me right now.
If gravity was too strong, would we be able to get up?
That's such a good question.
No, it really isn't that good a question. I mean, it's kind of obvious, right? I mean, if the 8-year-old should kind of already know the answer to that question, because she already knows that gravity is different on the moon, and gravity, she probably knows all that stuff. So, obviously, if there was more gravity, you wouldn't be moving very well.
No, we actually couldn't. The moon gravity is weaker, can almost float between footsteps if you look at the astronauts on the moon.
Yeah.
On the Earth, it's harder because it's bigger. If you go to a bigger, heavier planet, it gets...
So again, it's not about the size, it's just about the density. So that's all there is, okay? Realistically, just like the effect of gravity is really about velocity, in terms of orbits and all that stuff. One atom will orbit at the same velocity that the Earth orbits at. It's only one stupid little atom. Because it's all about how much you can absorb. If you're really small, you can't absorb much light, right? Well, gravity works the same way. If you're really small, you don't absorb much of the light, because you're really tiny. The anti-light, so to speak.
It's harder and harder, but there are stars that have died.
So this part, why go into this crap? This other alternative theory about a whole bunch of other crap that you have no evidence that happens.
that are so dense that there's no way we could lift our arms, no way we could step or walk. The gravity is just way too strong.
Yeah, how come we don't have any lensed images from those things? How come we don't use those? Go find one of those in space and use it as a little super lens to see. Because light is bent twice as much by gravity, by the magic Einstein theory. Bullshit.
Do you know how tall you are?
I'm in the fours,
In the fours?
maybe 4'3".
People think that while you're sleeping, your body has a chance to stretch out and gravity isn't crunching.
People think. That's how she did this. People think. Yeah, it's actually true, but I mean, why is it true? Oh, because we're hitting the earth. The earth is doing it to us. It's pushing into the earth that is compressing us. It's not gravity's fault. It's the earth's fault. We push into the earth pushes back. That acceleration doesn't happen like gravity. See, a piece of the tissue in your spine couldn't care how much gravity there is because it'll just move around evenly because there's not enough density for there to be a huge chemical pressure problem or anything else. There's no differentiation between how it treats one part of the cartilage versus how it treats the other part. It kind of moves the whole piece. Where when you crash into the earth, it has to push up through a bunch of chemical pressure, a bunch of physical pressure between chemical atoms, and they have to smash into each other. And that's what compresses something, is the unevenness. Gravity is very even. You hit the earth, it's insanely uneven, the pressure now. Now certain pieces of you have very high pounds per square inch, and other parts have very low. And that happens to your spine. At the bottom of all your cartilage, the earth is pushing back. That part has much higher pressure than the top part of the cartilage. Therefore, the cartilage over time, the chemistry, the atoms, start deforming because you're accelerating them with a crude force that has to go through the body. Gravity didn't do it. Pushing back on your feet or your ass, that's what's compressing your spine. But was she explain any of that? No. So, they're going to use the space analogy. And, the spaceman is actually in more gravity. It's just that he's not plowing into the earth. So he's in more gravity. He's being affected by gravity. Gravity is pushing on him from all sides. And now the earth isn't there. Well, the earth is there, frankly. But he's got a velocity in another direction that's keeping him in orbit. But let's say he's way out in space. So the earth isn't there creating much of a gravitational differential. And he's not relying on velocity to not fall into the earth. The point is those movements, first his velocity has already, it's not an acceleration, it's a velocity. So his body's already moving. That part's already been done. He doesn't have to accelerate or change speed. And all he's doing is changing direction. So changing direction isn't going to bend your spine, but changing speeds will. But there's lots of reasons the astronaut doesn't compress, even though he's in more gravity, technically. See, the universe, the empty space is where it's lightest. If I take all of the crap out of the universe, I'm in the most gravity I can be in. The crap in the universe is denying me access to the force. That's why I move, is because there's less force. If you're standing in front of me, I'm now getting hit by less stuff where you are, coming from your direction, because you're absorbing it, because the stuff inside of you is moving and it's using up energy.
You together, but when you're standing and walking or sitting, the gravity contracts your spine ever so.
So what? So again, the gravity didn't do it. Sorry, wrong answer. So the professionals really don't know what the hell they're talking about. The gravity didn't compress anything. The chemical pressure from the earth compressed you. The earth pushing you, your push into the earth pushes back. That pushback is expensive.
So slightly, so that in the morning you might be a little bit taller, than in the evening.
You might feel a little bit taller. So the truth is you are. So why is she saying you might feel and it seems like and it looks... No, we already know that's a fact. We already know that because of how we interact with gravity, that is always sitting or standing, most of the time, a lot of the time, when we're doing that, yes, we're being affected by the fact that the Earth is pushing us back up in a horrible way. Gravity's gently pushing us down, right? Pushing everything nice and even, little bits at a time. The ground is pushing back pressure points. It's pushing back with, you could think of it as the spiny needles. It's a bunch of spiny needles. Yeah, it doesn't kill us, but it's a lot of little pressure points. And over time, they're going to leave a mark. And the mark is compression of your goo.
See if it works for you.
La 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 la.
Oh, that was last night?
Yes. They say that astronauts in space, definitely their spine elongates. There were two twin astronauts, one...
So the other part to astronauts that makes the experiment kind of fudgy is astronauts are weightless, so they move around in all kinds of positions. They're not always in the same position. So even if gravity had a slight differential in it, even if it was imposing some acceleration and pushing from one side more than the other side all the time, they're defeating that because they're always changing their position. So it can't mean as much. But again, it doesn't really mean anything because your body reacts to gravity without creating pressure points.
Who stayed here on Earth and the other who went to the international...
So the word gravity is completely broken. It should be understood as gravity is the absence of something, okay, balance, and it's the real absence of force. There's a deficit in a force. It's not the presence of a force that's pushing you down, it's the deficit in the force that's pushing you into the Earth. The Earth is essentially colder than the space, if you want to look at it that way.
International Space Station. He was there for a long time, and when he came back, he was actually taller than his twin brother. Yeah, and that was because gravity wasn't compressing him all the time.
So again, wrong answer. Sorry, just completely wrong answer.
And he was floating freely in the International Space Station.
So again, he wasn't really floating freely. He was moving the same as the spaceship, which means that both were moving together, but they weren't doing any floating thing. The ship is not floating. Nothing's floating. It's all moving somewhere. It's just moving together.
And his spine just kind of elongated. After a while here on Earth, though, he'll readjust.
So his spine elongated. The right answer is his spine ceased to be compressed every day.
Go back to the same size. Have you ever heard of how gravity was discovered?
Mm-hmm.
Isaac Newton would ponder.
Well, why didn't you? She said, so why didn't you let her answer? I mean, I have to produce the show for them.
How does the Earth cause things to...
This got 4 million views, by the way. Which, compared to 29 million for a Wired show with a fucking how to cook. Cooking shows. 29 million views. This is a pathetically stupid planet.
The fall. There's a famous story that Isaac Newton was sitting under a tree and the apple...
Yeah, it's a famous story and everybody says, yeah, I guess it's just a story because we can't find any real facts to indicate it was actually true. That the inspiration of the apple was just what he used as a metaphor. He didn't acknowledge that the apple made him.
Fell from the tree and hit him on the head. Ooh. And he had an epiphany and understood.
See, even that story is even more ludicrous. I mean, the story that Newton saw an apple and then compared it to the moon is still a silly story that somebody just made up. But the fact that it hit him on the head is the real silly story. Of course that didn't happen. Ugh. I mean, come on. He wouldn't. He clearly he would have wrote that down somewhere. Oh, I figured out gravity because an apple hit me in the head. It was so funny. I never thought about it until the apple actually hit me in the head. And I said, what the fuck is that doing? Why doesn't the moon hit me in the head?
Did this law, this mathematical law for how that works. I don't actually think it's a true story, though.
I just told it for fun because we're having fun, right? The truth is about having fun. It's not about the truth. It's about having fun. I'm wearing lipstick. Yeah, she used to not wear lipstick. She used to be a scientist, Now she's doing something else.
Yeah.
But it's a good story. So Isaac Newton realized that even if your head...
Yeah, the kid was really impressed by that. You can see, right? I mean, she was really impressed by this baby talk. Yeah, thank you for treating me like a frickin' moron, bitch.
You will fall at the same rate as something much lighter.
Yes, because of how many atoms you have. And the whole point is that just like a tissue paper is not a very good blocker of light. A piece of tissue, more light will get through a piece of tissue paper. Right? So, I mean, we see the obvious analogies to how much is going to hit something based on how much hittable bits it has. So it has to have hittable bits to be hit. Durr. So exactly as much force as it can collect is what's going to affect it. So if it doesn't have very many collectors, it's not going to collect much force. It's not going to be, much force isn't going to be applied. But that's fine because, yes, that works for every single material object. Duh.
That's the same. Once you hit the ground, if you're heavier, you'll hit the ground with much greater force, but you will hit the ground at the same time.
So if we both drop down...
Right, you're hitting the ground with more force again just because you have more little bits moving. So, yes, more little bits means more weight, means more capacity to interfere with things. The feather runs out of capacity to interfere with the Earth because there's only a certain number of atoms and a certain number of electrons, and once their energy is used up, that's all there was, and so it can't disturb the Earth much. But if something has a lot more atoms, then it can do a lot more disturbing. That's all it is. How many atoms do you have to disturb it? So if you were sandblasting something, obviously if you just went poof with some sand in your mouth, that ain't going to do much. But, if you pull the trigger on a gun and shoot out, megatons of sand, then you can just about wipe anything out.
From a plane, we would both land at the same time, but you would land heavier?
Yep. So like a penny from the Empire State Building.
You would land proportional to how many electrons and protons you have going at the same velocity, and that's all it is. Just add up how many little matter bits you have, and that'll tell you exactly how much disturbing power you have. Period.
Will fall at the same rate as a bowling ball.
Oh my god.
Yeah. Amazing. Want to try it?
Yeah.
A light object? See how light that is?
So she's not explaining gravity, right? This is just explaining the effects of gravity, which they haven't changed in thousands of years. The effects have been documented by lots and lots of people, so not terribly impressive.
That's...
Very light?
Yeah.
And a heavy object?
Oh my god.
They look the same.
I didn't watch this part. It's making me a little queasy.
This is much heavier, right? Okay, so try it. Just try holding your arms out front and a little higher maybe. Give them a chance to drop and then drop them. Did they fall at the same time? Did they hit at the same time?
Oh, yes, I saw it. I could tell with my Superman vision that they hit the same time. Yeah, exactly the same. I saw it.
Time? So Isaac Newton, he was also the one who realized that that's the same force that keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. And that's a huge leap. Here he is looking at just things around him and then looks at the stars.
It's really not that big of a leap when you think about it, right? Because we already threw things on Earth. And so the thought experiment of Newton's was, well, what if I throw it hard enough? If I could throw a little harder, can I keep it going till it goes all the way around and comes back again? And can I keep it going? And how would I keep it going? What velocity would I need to keep it going? And that's all it really came down to oh, there is a magic number. There is a velocity that if I do throw it at that velocity, it'll never hit the ground.
And has this really big realization that that's actually the same force. So what have you learned today talking about gravity?
I've learned that the person that learned about
It's just terrible. You learned all wrong. You learned the wrong religion, okay? Jeebus is a lie, and this horse shit is a lie. But she never even said bent space. I mean, that's just such a cheat. I mean, to say, here, I'm going to tell you what we think gravity is, and then they don't even mention their little bent space silly fable. Let me see the kid's face when you try to explain that horse shit.
the apple.
Newton.
He was learning about gravity, just about what he saw on this planet. I also learned that if you drop one light thing and one heavy thing at the same height at the same time, they're both going to drop at the same time, but one's going to drop a little heavier than the other.
That's beautiful.
Drop a little heavier. You mean the heavier thing is going to be heavier and the lighter thing is going to be lighter. Yes. True.
Impressed.
So that was terrible, right? That was a terrible cheat. Oh, that's also not good. Ooh, commercials. I guess I could pause it or something. But it's booze.
So, Maria, you're in high school?
Yeah, I'm a junior.
Oh, well, it's like same girl grew up. It's just a coincidence.
And are you studying any sciences in high school?
I'm taking physics right now.
Do you think of yourself as curious about science?
Well, there are like some things that interest me and others that bore me, so it like depends.
What interests you?
Well, like I'm a gymnast, so like in physics they talk about like force and stuff, and then I think of like how I use
Force and
physics in
stuff.
like my own life.
What's your impression of what gravity is?
I think that if there's like no gravity, everyone would like float everywhere. It like pulls.
So again, just more bullshit, right? I mean, it's not about floating, okay? It's about the huge difference between a force that moves everything in you all at the same time and forces that don't. Forces that push on one thing really hard, and all of that energy has to somehow be converted into the rest of you. So all I have to do is, what's the analogy, right? Instead of walking on Earth, if we all walked with what do you call those leg things, stilts, and there were hand stilts. You know, we have to hold on to the pole with our hands, and then the energy goes through our arms, pulling us up. So all day long you're pulling, your body's being stretched, your arms are being made longer because all the energy has to go through your arms to keep your body up. It has to keep stretching your arms to do it. Then we'd have really, really long arms and really long spines, and we'd all be really tall and be really cool, wouldn't it? But it'd be completely different than this silly floaty bullshit. And the whole point is that we'd understand that it's just about all the other forces, the forces that aren't little invisible forces like magnetism and electricity and gravity. All the other stuff that is a force that has to go physically through the body in some uneven way. And that's all it's about. You feel the uneven ones. You don't feel the even ones.
Things down, and without it, like everything would just be like chaos.
So you're saying gravity pulls things down, yet we've launched things into space. Have you ever wondered how we do that?
But is it like a slingshot? Like if you pull something back enough, it'll like go in the opposite.
Oh dear, she's not too bright. She's not even getting the whole velocity thing. See, what comes up comes down unless you make it go round the Earth fast enough again so it doesn't go down ever. You have to get that. You have to go faster than the return velocity.
Opposite direction.
Well, that's true. We do use slingshot technology once things are out in the solar system. So, for instance, we use Jupiter and other planets so that when some of the spacecraft gets close, it'll slingshot around and it'll cause it to like speed up. And
it'll cause it to like speed up, like how? So she's supposed to be a scientist, right? She couldn't have added that, well, what we're actually doing is stealing some of the velocity of the planet. So the planet has a velocity in space, and we're going to try to take advantage of stealing a little bit of it and having it push our spaceship with its velocity. So it's going to drag us along, lose a little bit of its velocity, and we're going to essentially steal a little bit of the planet's velocity. Because that's what's really happening. It's not magical. You don't get it for free. You have to take it from somebody. It's that simple. You want some velocity, you have to take it from somebody.
Mostly around the Earth, gravity pulls things down. So when we want...
So again, all this pull down crap, pull, pull, pull. It reaches up with its little arms and it pulls us to it and hugs us and such. La 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 la. No, 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 no. Again, it doesn't even occur to them. They're so lost in this, holy ghosty religion of theirs that it doesn't even occur to them to say, I really shouldn't keep talking about these pull things because it just doesn't make any sense.
To send a rocket into space, when we want to go to the moon, when we want to send supplies to the International Space Station, the trick is to get something moving fast enough that it escapes the gravitational pull of the Earth. Have you heard the expression, what goes up must come down? Mm-hmm. It's actually not.
See, if you keep accelerating it, then you all you have to do is accelerate one little tiny bit more than gravity, a little more than 1g, and you can keep going forever and get away. But if you plan on turning the engines off, you're going to have a lot more speed than that.
True. If you throw it fast enough, you can actually get something that doesn't come back down again. And that's basically how rocket launches work. You have to get the rocket for the Earth to go more than 11 kilometers a second. Think of how fast it is. Just one breath, and it's gone 11 kilometers. If you get it to go that fast, it's not going to come back down again. So the International Space Station, which is orbiting the Earth, that's going around the Earth at like 17,000 miles an hour. It has no engines anymore. The engines are turned off. So it's just, they're falling forever. So once it's out there, it's not coming back down as long as it's cruising like that.
And does the gravity pull it, or is it just floating?
In a weird way, that is gravity pulling it. So have you ever...
Yeah, the only thing you need to understand is its velocity is not in the same direction as the gravity. So the two things are competing directions. So the gravity is pushing. Well, I don't have to explain it to you, but and it's just not enough change in the direction to change the direction enough, for it to either crash into the Earth or fly away.
Had a yo-yo where you swing it around like this. The string is pulling it in at all times, but you've also given it this angular...
Well, the string really doesn't pull either.
...momentum. And as long as you give it the angular momentum, pulling it in actually keeps it in orbit. And so the Earth is pulling it in at all times.
So again, this has nothing to do with explaining what gravity is, right? This is just, again, more talk about the symptoms of gravity. And the one symptom that the two important facts, it's push, and the second most important fact is it's a nuclear force. It's affecting the little tiny bits. And by affecting the little tiny bits, it's inert. You can't feel it.
That's why it doesn't just travel off in a straight line. It keeps coming back around. So it's funny, people think that the International Space Station is so far away that they're not feeling gravity. And that's not the case at all. They're absolutely feeling gravity. They're just cruising so fast that even though they're being pulled in, they never get pulled to the surface.
It's like that, the ride at the roller coasters where you go.
Yes, they're flying through space. They're just flying a trajectory that never crashes.
And it spins super fast and you can't feel it spinning fast, but
yeah, you feel pinned to the back. Yeah. It's exactly like that. There's something called the equivalence principle where people realized, especially Einstein, that if you were in outer space in a rocket ship and it was dark and painted and it was accelerating at exactly the right rate, you actually wouldn't know if you were sitting on the floor of a building around the Earth.
No, that's not true. So she just said accelerating at the right rate, and you'll feel the acceleration, so that doesn't make any sense. Unless the acceleration is opposing gravity, I suppose. But we didn't hear that part.
or if you were in a rocket ship that was accelerating.
It's crazy.
You ever had that experience where you're sitting in a train and the other one moves, and for a second you're not sure if you're the one moving?
Yeah, because I go on the train every day to go to school, but I never feel like I'm moving when I'm in the train. And then I'm like, wait, what?
That's because in some sense you're really not.
I never had that train experience, sorry. But whatever, fine. You know, that's what people have experienced. It's always occurred to me when the difference between a moving train and a not moving train, yeah, I can tell that difference.
Imagine you're in this train and it's going near the speed of light relative to the platform, but it's so smooth. Then you should be in a situation in which there's no meaning to your absolute motion. There's no absolute motion. So that if you throw a ball up, you might think from the outside of the platform, be confused that when gravity pulls that back down, it's going to hit you or something, but it'll land in your palm as surely as if you were in your living room. Isn't that kind of crazy?
Sense.
So imagine you are an astronaut.
So again, that's no mystery, the fact that it already has velocities in all the right directions, and so it's doing exactly what you're doing, which is you're not going to change until some force changes. Something has to change for it to change.
We're floating in empty space. You can't see anything. There's no stars, there's no earth. You can ask yourself, am I moving? There's really no way for you to tell. So you would probably...
Right. So again, there's no way for you to tell as long as you're not going to get moved by one of our physical forces. If I physically push you, you'll know. If I do something to cause that. But yes, if you're moved because you already gained velocity, well then, yes, all your parts are moving. Therefore, they're not going to see any relative difference. They're going to be all passengers on the train. One cell is going to be this passenger on the other seat, and you're going to be the passenger on this seat, and you're all going to just be moving on the train. So, yeah, you're not going to feel anything. But if I do accelerate you, you're going to feel that, the change. But if the change is gravity, you're not going to feel it because it's going to move him and you at the same time. And the same amount, and you're just not going to be able to feel your cells being disturbed because they're all going to be disturbed in exactly the same way. As long as your cells don't bang into each other, you don't know I'm moving.
Conclude, well, I'm not moving. So then your friend Marina comes cruising past you, and maybe she's going thousands of kilometers a second. And you say, Marina, you're cruising at like thousands of kilometers a second. You're going so fast.
So this is laws of motion stuff that doesn't really have anything to do with gravity, right? Yeah, right.
But she had just done the same experiment. She was just floating in space, thinking, am I moving? There's no way to know which one of you is moving, and there's no meaning to the absolute.
So again, there is no, when she says there's no way, she did it by, prefacing you can't see anything. But if you can see other things, then you can know you're moving relative to them, and you can certainly know that there's something changed. And your deduction is, well, if everything else starts moving, why would I think I'm the one not moving? That would be kind of silly. Everything else just spontaneously decide to take off? No. That'd be a silly conclusion.
Motion. The only thing that's true is that you're in relative motion. That's true. You both agree you are in relative motion, and that's clear.
So again, this doesn't even work either. Like I said, with the light clock, you can tell. You just can't tell. We can't. All right. We don't have fine enough instruments to do it. But the fact is that a beam of light will tell you whether you're moving or not, because the beam of light isn't going to pay any attention to complex motions and having any other motion than just doing one motion, which is it's going to leave and it's going to go travel the speed of light. It's going to travel in a straight line. And if the sides of your vessel are moving, you're going to see them moving because the beam of light isn't going to hit the right spot. It defeats their physics. That the thought experiment does destroy this silly idea that there's no experiment you could. Yes, there is.
But neither of you can say it's actually you who's moving and I'm stationary.
So again, she's saying that she knows this, that there's no way to analyze your molecular structure. Like there's no way that with any technology I could ever know who's moving, when I would argue that, yes, of course you can know, because movement is a real thing, and it really happens to atoms, and they have to get into complex arrangements to be able to move, and you're going to see those arrangements. Things can't have velocity without paying some price for it. It changes the thing. The wrench moving through space is different than the wrench sitting on Earth. If you could look at the little tiny bits inside, you'd see that the neutrons and protons of the one wrench are arranged differently than the protons and neutrons of the other wrench.
I don't even know what to say to that.
So let me tell you where it gets really crazy. So let's say you and Marina are floating in space, and you can't tell who's moving.
So this isn't gravity, right? This is now she's talking about relativity. I mean, it's just, what the fuck? Oh, phooey. I shouldn't have done that, I guess. Can't hit the pause and play
Let's
button.
say you both see a flash of light. The flash of light comes from somewhere, you don't know where. So you measure the speed of light to be 300,000 kilometers per second. But here comes Marina, and she's racing at the light pulse as far as you can tell. Two cars driving towards each other seem like they're going faster towards each other than somebody who's standing still relative to one of the cars, right?
Yeah.
So you would say, oh, Marina's going to measure a different speed of light. But she comes back and she says, nope, 300,000 kilometers per second. Because from her perspective...
So that doesn't work, right? Because then when the two of them meet up, they're not going to be the same age and all that kind of crap. So you've broken time, you've broken the measuring tool. So you're not measuring the speed with the same ruler, so what's the point of the conversation? But the light didn't change. She should, okay, measure the speed of light differently, because obviously she's taking distance away from how long the beam has to travel. So obviously how long the beam was in space is a different amount of time than the beam was in space for the other person. So the point is, there's just no point in having the conversation in this silly context that we're going to change entire basic functions arbitrarily and then put them back to normal again. So again, she already broke the normal. She should just say, well, you and her will never see each other again, because she's going to be on a different destiny in terms of her biological evolution is different than yours.
She's standing still, and the laws of physics had better be the same for her. The speed of light is a fact of nature.
So again, yes, of course it's a fact of nature, and if you make a beam travel less distance, it'll take less time to get there. You can't change that. If you change the distance, you change how fast or how far the light traveled. You change how much time it took, period. You can't undo it with this pretense that the perspective of the observer can dictate some I changed that rule. You can't change that rule.
It's as true as the strength of gravity. And the two of you are in this quandary because if one of you is the preferred person who correctly measures the speed of light, that ruins everything about the idea of the relativity of motion.
Oh, here we go. So this is about relativity. It's not about gravity. I mean, it's just too stupid. They're not the same thing, frankly. They really aren't.
Which one of you should it be? So Einstein decides they must both measure the same speed of light. How could that possibly be the case? And he thinks, well, if speed...
It can't possibly be the case. That's the whole point. It can't be. More distance is a real thing the light has to do. If it has to travel more distance, it will take more time, period. End of subject. This is too stupid.
Speed is how far you travel, your spatial distance, in a certain amount of time. Then there must be something wrong with space and time. And he goes from the constancy of the speed of light and a respect for this idea of relativity to the idea that space and time must not be the same for you and for Marina. And
yeah, well, whatever. It's just absolute nonsense. So again, even if we project some of this to be true, that somehow by having velocity, your metabolism changes and you process the universe slower, it doesn't change the fact that one of you actually is moving faster than the other. It doesn't change the fact that you're dilated, they're not. It doesn't change any of those facts. So it doesn't make the world different. It doesn't make the rest of the universe unaware of the fact that things have velocity and things don't. That there is something in the universe that may not be moving at all, and there may be something in the universe, a material thing, that's moving faster than anything else. It doesn't change that. It's one universe, and everything has to live in the one universe. There's nothing else to live in. There's nothing else you can function in. And the simple truth is, there is a truth. Either you fucked up standard time, or you haven't. And when you fucked it up, you just look out the window and you can see you fucked it up because the rest of the universe is buzzing by. At 10 million miles an hour, it's just swoosh. You'll be able to see that you're dilating.
That's how he gets to the idea of the relativity of space and time. You have the best expression on your picture. It's pretty wild.
So it's too bad she didn't explain gravity, right? I mean, just handle the simple subject. No, she had to throw relativity in. It's just disgusting. Ew.
But that is a starting point, actually, of the whole theory of relativity. That starting point leads to this complete revolution in physics where we suddenly have a big bang and black holes in space-time.
That does not. The fucking, the Big Bang has nothing to do with relativity. That's just more horse shit. Obviously that's just a complete perversion of redshift. And the fact that there is energy in the universe, so what? I mean, it doesn't mean that we're seeing something. I mean, the whole distance thing just doesn't work. If it was an explosion, we're sitting here saying that we're a big chunk of the explosion, a big hard piece. So we obviously move less far. The little stuff moved much faster. How the hell are we seeing the little stuff? It already blew right past us, right? I mean, the little bits of a nuclear bomb go flying out, the radiation and other stuff, really fast. The buildings go tumbling out, Oh, anyway.
From that one simple starting point. So is your impression of gravity different than when we started the conversation?
Yeah, because, I knew that, when I was on the train, I didn't feel like I was moving, but I didn't know, why.
I didn't like, I likey, don't like.
That it was a thing, and I wasn't crazy.
And it's a really deep principle. And what about the theory of gravity?
I don't know.
There's just no deep principle. The deep principle is that you don't feel your velocity. You feel acceleration. And you only feel it when it's imposed on you in a sloppy, crude, bad way. You don't feel it at all if everything is pushed evenly. By forces.
Usually when I just hear gravity, it's, from my coaches. But I didn't know, it was, all these things.
Mm-hmm. It's like a big paradigm.
I'm sure she knew what paradigm meant. All right, well, we'll save this for later, I suppose. Maybe we'll do the rest of this, and I'll suffer the pain. So, so I'll just do the blackboard thing really simple, just to explain one more time the rational explanation for what gravity is. Okay, what causes it? That's what they were supposed to talk about. And they didn't even touch upon it. She didn't explain anything about gravity. She explained what it's like to be pushed by the earth, pushed back by the earth. Which just isn't the same subject. Alright, to turn this on. Alright. So the simple explanation is this can be thought of as an equilibrium problem, a heat problem, a lot of different ways to look at it. But the simple point is that the universe already has this force in it, and it's going in all directions. So wherever you are, there's an even amount of it theoretically. Oh, you can't do that, Gary. You gotta remember, you only a part of this board is visible. This part to this part. Okay. So I can, that's not very much. Can't be that small. What did I put the line there for? This much to this much. Anyway, I erased it again. Alright, never mind me. I'm trying my best. Okay, so the force is coming from all directions. If there's camera keep dropping or something? am I missing something? Yeah, it must have dropped some more. Okay, well, we'll just pretend it's right. All right. So it's coming from all directions, the light that's on in the universe. And the simple argument is when there's an object in the universe, somehow it's absorbing the light. So light goes into everything, okay, force, energy, everything material. And somehow less comes out. Now you can understand that if less is coming out than went in, everything's going to be darker than the background. No matter which side I look at it from, it's always going to be darker than the background because it's eating some of the energy. And the simple explanation for that is that the matter, the stuff we call, the electrons and the protons, they don't have any will of their own. They don't go anywhere, they don't do anything, they have no engines, they have nothing. And they have to be moved by those little arrows, that force. And what happens is the force is hitting them from all sides all the time. They're getting hit, and they move. And when they move a little slower than the force that hit them. Right? And if I just say this force, when it hits matter and moves it moves it at 10% of the speed of light. Well, if I hit it again before an opposing force hits, then you could say that one also is 10%. But it's 10% of the 90% that's not moving, right? So then I can just say 10% of the 90%. So this will only be plus 9%, And then it goes down to 8 and 7 and 6, and then and it's the same thing as the Einstein curve. Well, it's a similar thing. The amount that you affect something goes down, so it's the opposite of the curve. Goes down, diminishes, as you go faster and faster. So as I move the matter faster, I can affect it less and less by adding more force and get less and less new velocity out of it. So I can never get this thing to the speed of light. So it explains why you can't move matter faster than the force. Simple explanation. Because you're really consuming force. So by moving the matter, the force is slowed down. So for a little period of time, it's not going C anymore. Not C. Somebody complained I was using the less than sign wrong, but I really don't think so. You have to point at the thing that's less, in my opinion. So it's going less than C when it's moving, and the force is pushing it. So the force is now going less than C. So you can understand that that's a diminishment of what energy is in the universe. So every time an electron moves, it gets jostled by the force, jostled by the environment that's pushing from all directions, gets hit by little photons of energy from the universe, the little energy from the universe, the invisible photons of the universe. Every time it gets jostled by one of those, it steals a little bit of the energy of it by forcing it to push a big clump of matter that doesn't move as fast. And so a little bit of energy is being absorbed to create heat. Now, it's sort of conservational because, the matter moves, so that does generate something as a byproduct. But the fact is you can never give back the force the speed you took away from it. You can never give it back the time it took it to do that. Just like in my life, if I have to reboot my computer because Linux is a piece of shit, no, it really isn't that big a piece of shit, but it is a piece of shit. I can't get those 40 or 50 seconds back, right? It might be a minute and 20 when you end up kneeling down to hit the button and blah, blah, blah. I can't get that time back. That time is always gone. So if I'm going to be a concert pianist or something, that's one little key I didn't get to practice because I lost 120 seconds rebooting the computer. And that's what's happening in the universe here. The force loses a little bit of its I can do shit because it did shit. And by doing shit that doesn't really matter, I mean, if I move an electron from here to here, and then I move it back over to here again, and then I move it back over to here again, I move it back over to here again, I'm not changing anything. I'm not doing any work. Oh, well, sorry, I should have drawn it down here. I move it here to here, and then I move it back to here again, then I move it back to there again, then I move it back to there again. I'm not accomplishing anything. I'm not accomplishing, not changing, not doing. There's no work involved because I keep ending up where I already am. So nothing changed. But you can't change the fact that the force had to do all of this work. It had to kneel down, press the button, blah, 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 wait. It slowed it down. So the simple answer is that every little piece of matter consumes energy by moving. It consumes the force, a little bit of it. And so everything made out of that stuff moving is going to be radiating less energy than goes in. More energy will go in, less energy comes out. That means everything is darker than the universe itself. The universe has this much force in it. You radiate back this much. You know, you're radiating back 3.9. It gave you 4. So you just think of it the opposite of the way it looks. The the matter bits are reflecting light. You see those. And the universe is dark. Just reverse it. The universe is light with force, and the things that we see as being light are actually dark. And then you can understand it. Simple. They breaking equilibrium because the force doesn't come out with the same. Its total energy has been, a tiny bit of its total time has been eaten, okay, doing work, moving matter, and that moving matter doesn't get anything done, so it just doesn't, it's just a loss of time, a loss of energy, a loss of the speed of the force. And therefore it has less momentum after than it had before, because the total distance it will travel in its lifetime is less distance, right? You could just think of it that way. Every time it's pushing a piece of matter, it's reducing its total distance accomplished in its existence. And the amount of distance over time is its momentum. So it lost a little bit of momentum by being forced to move slower than the speed of light. By being obligated. Force, that's the wrong word. Anyway, that simple explanation explains what gravity is. It's just, there's no push, there's no pulling involved, there's just an absence of the equal push. It's taken away a little bit of push, and therefore the other push that already existed pushes you into the earth. Alright, simple explanation. So, till the next time, and such, and so forth and whatnot.